Hello again. Our next topic is acids and bases. This will probably take 2 to 3 longer videos to get through. I'm going to pretty much follow what the book is discussing. However, I'll go into a little bit more detail. The chapter 10 referenced is what I'd like you to read, and also the other textbook has some helpful information. So I would also review the other textbook, the chapter on acids and bases. I don't remember the name of the other textbook, but just click on both links in the syllabus and go to the chapter on acids and bases, and please review those chapters because everything in those chapters is pretty much what I'm going to discuss here, and I'm hoping to finish acids and bases, or at least you should finish it at home by mid next week and move on to organic chemistry later next week. So we have a lot to talk about today, and I think what I'm going to do is give you the basics of acid-base chemistry, give you some of the theories, and I'll give you a few demonstrations here. There's going to be a lab on what's called an acid-base titration that I'll post over the weekend that you'll have to work out. It's not terribly difficult. I'll give you a video with that. Let's jump right in here. And we're all familiar with acids and bases. We use them every day. They're in our food. They're in our cleaning products. They're everywhere, essentially. So you're going to see a lot of reactions written like this. Acid plus base gives you a salt and water, essentially. That's the general form of an acid-base reaction, but it doesn't always occur that way. You'll see here in this reaction, I actually have a water molecule acting as a base. Water, as I'll discuss tonight, is unique. It can act as an acid or a base. It's one of the few substances that can actually do that. That's a property called amphoteric. But there's two ways to write an acid dissociation. This is one way to write it, and we're going to talk a lot about that tonight. This is just hydrochloric acid dissociating into a proton and a chloride ion. But it looks a little more complicated than that because it's got a water molecule written. Water is the key to why acids behave as acids and why bases behave as bases. If you don't have water, they won't behave as acids and bases. Water is the main reason why they do that, and we'll talk about that. Let's just go over some basic definitions for a little bit here. So acids, the most basic definition is that they release protons. So an H plus has a few names. We can call it a hydrogen ion or a proton. The OH minus that bases release is called a hydroxide ion. We usually call acids proton donors, and bases we'll call proton acceptors, or we can view bases as something that supplies hydroxide ion to a solution. There's going to be two main theories of acid-base chemistry that I'll talk about in a few minutes. Acids and bases can be either strong or weak. Now that's a relative term, just like in equilibrium. There were things that were strong and weak. Strong acids or bases completely dissociate. Dissociation is another word for ionize. Ionize just means the molecule breaks apart into a positive and a negative charges. Weak acids do not ionize or dissociate nearly as much, not completely. So here's one way to view that. I want you to remember all the strong acid formulas. There are, I think, 6 or 7. HCl, HNO3, HBr, HI, HClO4, and H2SO4. And actually, if you could throw in HClO3 to that group as well. That's called chloric acid. That's called perchloric acid. But when we write an acid dissociation, you'll see it written like this often, where the acid is written with an aqueous symbol, meaning it's dissolved in water. It breaks apart into a proton and the conjugate base, or the nitrate ion, for this particular acid, nitric acid. We say that reaction occurs essentially 100% So notice there's no arrow in the reverse direction. It is not an equilibrium. It's essentially a complete reaction. Strong bases react the same way. They're mostly hydroxide-containing salts, sodium hydroxide, potassium hydroxide, lithium hydroxide, etc. You'll notice that the metal, they're an ionic compound, so they have a metal from the first two columns of the periodic table, and they're bonded to one or two hydroxide ions. You could also have aluminum hydroxide as part of that group as well. That's in column 3 of the periodic table. But again, they're all metal hydroxides. Those are the common strong bases. When they dissolve in water, which we usually write with a water above the arrow, they break apart. They're completely soluble in water. But they're not like your run-of-the-mill salt like sodium chloride. Hydroxide ion is a very, very strong base. It's probably the strongest base that can exist in solution. Now, when I say in solution, I mean dissolved in water. Or water is the solvent in all these examples I'm talking about. But bases ionize it completely to 100% as well. Now, contrast that with, for instance, a weak base, NH3. NH3 is a weak base, so we have to use this equilibrium symbol. It does not completely go to the right. It actually has, it's probably, if you had to write these arrows correctly, you'd write a large arrow to the left and a very small arrow to the right, meaning that the equilibrium lies far to the left. Most of the things that exist at equilibrium are NH3 and H2O. There's a little bit of the what's called the conjugate acid of ammonia, which is NH4+, and a little bit of hydroxide ion. But ammonia is considered a base because it produces hydroxide ion. It produces it indirectly. These produce hydroxide ion simply by dissolving in solution. Ammonia produces it by reacting with water. That's the difference between a weak base and a strong base. So we say that weak bases are much less than 100% dissociated. Now, organic acids, or weak acids, are things like we talked about in the equilibrium chapter. They are molecules that contain carbon. They're like acetic acid is the acid that's found in vinegar. It has two carbons in it. Benzoic acid has 7 carbons in it. But they're based on carbon, and they have they're weak acids, meaning that they don't completely ionize like nitric acid would. So we have to express the strength of the acid with this value called, with this equilibrium constant called Ka. It's just an equilibrium constant like you've written before, but it has a subscript A, meaning for an acid. And there's a new term I want you to become familiar with called pKa. That's another way of expressing the acidity of a solution. The lowercase p is the same p that is found in the term for pH. It's a mathematical instruction to say take the negative logarithm of something. And I'm going to discuss what logarithms are this evening as well, because you have to have a basic understanding of a logarithm to understand fully the pH scale. But as the Ka of a weak acid increases, the pKa decreases. So they're just different ways to express the same thing. A larger value of Ka means it's a stronger acid. A lower value of Ka means it's a weaker acid. So in this pair of acids, benzoic acid would be the stronger acid, and acetic acid would be the weaker acid. We don't use Kas for strong acids because they don't really have any meaning. The Ka for nitric acid would be 1,000 or more. So it really doesn't matter what it is, because since it's such a large number, there's no back reaction. This small value of K is a reflection of the fact that the weak acids and weak bases exist as part of an equilibrium. So there's a competition between the product side and the reactant side, which you have to express with this number. In general, we write the dissociation of a weak acid, just call it HA, aqueous. It's dissolved in water. It breaks apart into a proton and its conjugate base, the basic form of the acid. Here's how we define Ka. It's an equilibrium constant, just like the equilibrium constants we talked about a little earlier. It's the concentration of the products divided by the concentration of the acid. Notice all of them are aqueous, so that means they all can have concentrations that change. Therefore, they must be included in the Ka expression. And the Ka for a particular acid, let's just say benzoic acid, is 6.3 times 10 to the minus fifth. That just means if you take at an equilibrium mixture of benzoic acid, if you have an equilibrium mixture of that, and you were able to measure the proton concentration and this concentration somehow, and you knew the initial concentration of the benzoic acid, and took this ratio, you would end up with a number of 6.3 times 10 to the minus fifth. That's a really small number. All it really means is that these concentrations of the products are very much smaller than the concentration of the reactants. So it's just a ratio, so to speak. Another way to say the same thing is to use the pKa of this. So when you say pKa, it says the little p means take the negative logarithm of that number, and when you do, you get a positive 4.20. Notice that's another thing you have to keep in mind is if you have two significant figures in your measured value, in your equilibrium constant, if you have two significant figures, the power of 10 doesn't have anything to do with it. That's just telling you where the decimal point is. But if you have two significant figures here, you need 2 decimal places in the logarithm. That's important to remember. That's why I reported as 4.20. This number 4 is just a reflection of the power of 10. It's not a 5, but because this number is more than 1. This isn't a math class, so I'm not going to get too involved with that. But that number has to do with this power, this number here, this 20, these digits have to do with those number of significant figures there. And you'll see what I mean in a little bit when I do some examples of pH. So let's just go over what some common acids and bases that you might have come across are. Here's the formulas of a bunch of common acids. Here's the 3, 6, 7 strong acids that I hope you've memorized by now. The rest are weak acids, and there's many organic acids that are weak. Acetic acid, which is this. And I'll draw that formula a little clearer later. That's just the molecular formula. It doesn't really tell you the structure of the molecule. Lactic acid, which is the acid that builds up in your muscles when you exercise, is a weak acid. Sulfurous acid, nitrous acid, phosphoric acid, that's in soda pop. Carbonic acid is the acid that's also in carbonated water. It's also part of your blood buffer system. The strong bases and the weak bases are, as I said, the metal hydroxides are strong. There's many weak bases, more than I've listed here. Calcium carbonate, which is essentially chalk or limestone. Sodium bicarbonate, that's baking soda, that's a weak base. It's a salt. Notice these are all ionic compounds. You don't really consider acids ionic compounds. They behave like ionic compounds in that when they dissolve in water, they break up into a positive and a negative charge, just like these ionic compounds do. When these dissolve in water, at least this one, this one, this one, this one, this one, this one, and that one, when they dissolve in water, they break apart into a metal positive charge and a negatively charged polyatomic ion or an hydroxide. This one is a base indirectly. As I showed earlier, ammonia is a base because when it reacts with water, it forms hydroxide indirectly. So that's a base. It doesn't look like it's a base because you think all bases have to have OH as part of the formula. That's not true. That was a limitation of one of the early theories of acid-base chemistry called the Arrhenius theory. So they had to modify it and have a little more sophisticated theory, which I will talk about shortly. Some of the other properties of acids and bases are on this next page of your notes. Acids taste sour. The word, I think the Greek or Latin word for sour is acidus, so that's where we get the word acid. The bases on, acids and bases, there's a lot of symmetry involved. They balance each other out in many ways. Acids taste sour, bases taste bitter. The word alkali is another word that describes basic. You might have heard alkaline batteries. Well, those are batteries that are based on basic chemical reactions that have basic pHs. That's an Arabic word. Bases feel slippery because when you spill them on your skin, you're actually making soap out of the oil of your fingers, because bases are used to make soap. Acids turn blue litmus paper red. Bases turn red litmus paper blue. You see how it always kind of, there's a symmetry of how they're related to each other. Acids and bases are both electrolytes. That means they dissolve in water and release ions. The pH of acids is defined as less than 7. The pH of bases is greater than 7. Here are some of the common reactions of acids and bases. Notice that the most common type of reaction of an acid and a base is they make a salt and water. But that isn't the only type of reaction that an acid and base can undergo. So HCl plus NaOH gives you sodium chloride and water. They're also called double displacement reactions. They're like the precipitation reactions we discussed early in the course, where you have two ionic compounds coming together to give you a precipitate and something else that's soluble. Same thing's going on here. The H of this acid goes with the OH here, you get water, and the sodium of here goes with the chloride here. They just switch places. There's nothing real fancy going on here. Sulfuric acid, so the hydrogen ion of sulfuric acid goes with the OH to make water. You just get 2 of them because there's 2 protons here. You get sodium sulfate as the other product. So there's your salt. Salt is an ionic compound. So nitric acid can react with aluminum hydroxide to give you aluminum nitrate, your salt and water. Notice the number of water molecules you get is the same number as the number of protons or hydroxide. So you have to remember how to balance these things out as well. Reaction of an acid with a more active metal, called single displacement or oxidation reduction reactions. We've seen these before. Acids dissolve metals like magnesium. Magnesium dissolves very well in acid to form a soluble salt, and it generates hydrogen gas. Copper does not react with these acids, so that's why when we did that lab with the copper cycle of copper, you had to add a special acid, nitric acid, that actually had oxidation powers. So it wasn't your run-of-the-mill redox reaction. It was a more powerful acid. Reaction of acids with carbonate. These are the type of reactions you might see if you need to take an antacid tablet. Excess acid in your stomach, for instance, is excess HCl. This is the acid that's in our stomach. And if you have indigestion, you have too much of this around. So we take these antacid tablets, which is at any base. Common antacid tablet would be calcium carbonate. You could take magnesium hydroxide. Sodium carbonate isn't real. I don't think that's an active ingredient in many antacid tablets, but you might have noticed that when you take an antacid tablet, you generate a lot of gas. That's because you're forming CO2. Antacids or bases that contain carbonate will generate CO2 gas. How does that happen? Well, the same way as it happens up here in these reactions. The proton of the acid, whether it's HCl or H2SO4, will combine with CO3 to give you H2CO3, which is carbonic acid. But carbonic acid is unstable at room temperature, and it decomposes into water and CO2. That's where the gas is coming from. But in any case, the other product is going to be your salt. So this would give you sodium chloride. This would give you calcium sulfate. This reaction here, sulfuric acid and calcium carbonate, would give you calcium sulfate and water and carbonic acid. But you're also generating water. You see in most acid-base reactions, you generate water as a byproduct, but not in all of them. And then, so you might have seen another way to represent. Now, I might use this notation a little bit in these videos as well, as these arrows to show you the movement of electrons. So, for instance, if you take acetic acid, which is the main acid in vinegar vinegar is 5% of this in water, and you add sodium bicarbonate. This is the structure of sodium bicarbonate. This is one way to represent an acid-base reaction. The acid is the proton donor, so it's going to donate this hydrogen in blue to this compound here. But what happens is this compound will make, when it accepts this proton, it will fall apart because that's H2CO3. So this is how you get the CO2. This electron pair moves here, this bond breaks essentially, you get H2O, you get a CO2 molecule, and you get sodium acetate. And you can see that if I just took vinegar and bubbled it onto baking soda, you get that very vigorous reaction. This is the same reaction that occurs when you bake bread. You know, you use baking powder or baking soda to make bread or cookies. That's the reason why they want you to add baking soda and vinegar or acid to a recipe to generate CO2 bubbles. The CO2 bubbles cause the food to have it's called a leavening agent. It traps gas, CO2 gas within the food. Now let's go into, I've given you a lot of reactions here. Let's talk about the two main theories of acid-base chemistry. What are they? Well, the first theory is called Arrhenius acids. Got a little water on there, sorry about that. Again, some common acids you might have come across in everyday life: orange juice, aspirin, soda, lemons. Those are citrus fruits like lemons and oranges. Soda has carbonic acid. Aspirin is actually an acid. Acetylsalicylic acid. Orange juice, of course, is acidic. Common bases that you might come across in your house: Drano, which is drain cleaner. It contains sodium hydroxide. Ammonia, most cleaners are bases. Food preservatives are mostly bases. There's acids in the atmosphere, mostly formed by gases from emissions from industry. So SO2 and NO2 are given off by car exhaust or out of industry. They can get oxidized in the atmosphere to the SO3, and then they can combine with water to give you sulfuric acid or nitric acid as acid rain. Bases in the outside or in the ground or in the water are things that have negative charges: carbonate, phosphate, bicarbonate. They're found in rocks and in soil. These will dissolve in water as well. This is why some areas of the country are resistant to acid rain, because if they have a lot of these bases in the soil, they can resist added acid because these will neutralize the added acid. But to explain how acids behave, the first theory that became popular was proposed by a Swedish scientist named Svante Arrhenius, and his definition is the most basic. He viewed acids as just something that breaks apart into two pieces. Acids release a proton, a hydrogen ion, to solution, and they're limited to water, to aqueous reactions. And bases are something that supply hydroxide ion to a solution. So that's the limitation of the Arrhenius theory. It only works for aqueous solutions. So we needed a more general theory of acids and bases that would apply to reactions that didn't necessarily involve water. And that's what's called the Bronsted-Lowry definition. So anything that's an Arrhenius acid is also can be considered a Bronsted-Lowry acid or base as well. So the Bronsted-Lowry definition, I think the camera moved a little bit there, is this. It was proposed in 1923 independently by two different scientists. That's why it has that dashed name. Bronsted-Lowry. Johannes Bronsted was in Denmark and Thomas Lowry was in England. In the year 1923, they both proposed this new idea of what acids and bases are. It's a more general theory. Acids are viewed as proton donors, and bases are viewed as proton acceptors. So when you view an acid as a proton donor, we usually write a strong acid dissociating like this. It just completely breaks apart into H plus and NO3. Here's some examples of some other acids. These are weak, those are strong. another way to write an acid dissociation is like this. So the only difference between this reaction here and this one is that I have a water molecule written. They're both expressing the same thing. A strong acid is behaving as a strong acid because it's supplying 100% protons to the solution. So it means if you have 1 mole of this in the solution, you'll get 1 mole of protons. They're either going to be drawn as an H plus or as an H3O plus. This is really the more correct way to write an acid dissociation of a strong acid. It means that the proton is being given, the proton of the acid is being given to the water. So the proton of the acid has to have a reason to leave the HNO3. The water essentially pulls it off by acting as a base. Water is unique in that way. It can act as an acid or a base. In this case, it's acting as a base. The oxygen is accepting the H plus, and it becomes H3O plus. That's called the hydronium ion. And the HNO3 loses its proton and becomes a nitrate ion. Notice that the charges in either case balance. 0 on this side, 0 on this side. 0 here, 0 here. So whichever way you choose to write an acid dissociation, it doesn't really matter. They're both correct. This is just a little more correct, meaning that it's showing you that the water is the key to why this is behaving as an acid. In the Bronsted-Lowry theory, bases are not things that necessarily produce OH, like in the Arrhenius theory, but they're things that are proton acceptors. So this theory just views acid-base chemistry as what's happening to the proton. Is it being donated or is it being accepted? Things that accept the proton are bases. So ammonia, NH3, is a Bronsted-Lowry base because it accepts a hydrogen from water. It pretty much, this lone pair here will pick up a proton to become NH4 plus. Notice the charge went from neutral to +1 when it picked up a proton because protons are positively charged. And what was left with the water was a hydroxide ion. So there you go. There's why these are bases. They're producing hydroxide indirectly by reacting with water. We draw these as equilibria, the plural, because they are weak bases. This is a strong acid, so there's no back reaction, just a forward reaction, a left to right arrow. Weak bases and weak acids have the equilibrium arrow that's needed because if you're able to measure the concentrations of all these things, you'd actually measure amounts of all of them. They'd all be present. Other examples of weak bases are bicarbonate ion, sulfate ion, phosphate ion. The nice thing about this theory is that it applies to gas phase reactions as well. So there's no water involved here. Ammonia gas will react with hydrogen chloride gas to give you ammonium chloride. This is actually a lab we do in another course at our campus. It's you put a cotton ball saturated with ammonia at one end of a tube, and at the other end of the open tube you put a cotton ball saturated with hydrogen chloride acid, HCl, and the gases float down the tube and meet somewhere in the middle, and they form this white cloudy precipitate, and that's a way to measure the speed of the molecules. But there's no water in this reaction, so that's why this theory here is a better theory. It doesn't require water to be present. Now, some more terms I'd like you to be familiar with in how we discuss acids and bases are what's called conjugate acid-base pairs. So it just means that a conjugate acid-base pair are related by a proton. That's it. So you'll see water here is, these aren't really chemical reactions, they are acid dissociations. But we'll just view them as reactions for the time being. So HCl reacts as a strong acid, so there's just an arrow left to right. But we call that the acid, of course. The water is the base. And the acid, losing a proton, becomes a chloride ion. So the acid becomes a base. The water, which picked up a proton from the hydrogen chloride, or the HCl, becomes what's called a hydronium ion, becomes a conjugate acid of this. It's a little confusing, but HCl and chloride ion are one conjugate acid-base pair. They only differ by a proton. Water and hydronium ion are another conjugate acid-based pair. They only differ by the presence or absence of a proton. So that, again, is a strong acid. We would say it's 100% ionized. I think I'm getting a message that I'm reaching the limit on my phone here, memory, so I'll have to stop this video and continue on in video number 2.